Awesome. I should be live now. Hey everyone. Thanks for joining another week of the Deep Learning Book study group. Let me make sure I can hear myself and everything is okay. I can. Awesome. Let me take off my headphones and get started. Welcome back, everyone. If you're just clicking on this video, this is not a substitute for the book. This is rather a study group for the book, and I'm talking about this book, a deep learning book by Ian Goodfellow et al. If you are returning, I had promised we'll be covering chapter 4 and 5 today, so that is the intended goal. There's one minor correction. I wanted to cover machine learning basics chapter as well, which is the fifth chapter. Um, but there's not a lot worth covering in that chapter. It's pretty straightforward. So instead of spending a fair amount of time there, I would just leave it like that. I'll just probably point out all the topics that exist inside that chapter, and we'll probably end it at that. So the title of today's meetup was a bit misleading, if I may. But I did read through all these chapters, and I'm actually almost right where we're supposed to end the study group. I don't think this is worth our time, so I'll skip this. That being said, if you have any questions about any chapter whatsoever, you're welcome to post them either in the comments here or on our community at h2.ai. So please feel free to post the questions anywhere. And here's the link again for that. There's one more disclaimer that I need to mention. I also intended to cover the Pythonic bits from chapter 3 until 5 today, but that'll probably happen in the next live stream. I was on the road for most of the last week and I didn't get a chance to do that. So, again, for that, you can keep an eye out on the GitHub repo, which is the first link in the description. So, you can keep an eye out there, and whenever I push the notebooks, you can check those out. So this is the repo, and I also wanted to mention Ishan, who's been working on PyTorch notebooks for the study group. So I thought he was a Kaggle Grandmaster. He's a Kaggle Master, but I'm sure he'll soon be a Grandmaster in the notebooks category. So Ishan will also probably be contributing Torch notebooks, which you'll see in the repo soon. So you're welcome to keep an eye out for that. Apart from that, we can get started. Hey Mohammed, thanks for joining. Nishchay told me he was caggling at this time, so I don't know what he's up to. But maybe he can host the session. He quite likes this book. We were just chatting about this book before the live stream. Okay. So here's the agenda. We usually cover one chapter every week. Was supposed to be two chapters, but it's only going to be one. The second one really doesn't need much coverage. I assume all of you are practitioners. All of you are familiar with most of the jargon mentioned there, and it's probably not worth your time if I re-explain the concepts instead of you just reading them. The end goal is to take this knowledge. So the chapter for today, it talks about Hessian matrices, it talks about Jacobian matrices, and the end goal is like to understand what these mean, and whenever they pop up in a paper or a research paper that you're trying to dissect, for me that's the end goal. I should be able to like instantly look it up and have like a flash reminder. Oh, okay, this is what that means, and I don't skip the mathy bits and researchy jargon when I'm going through that. So that is my end goal. And I'll also be, as I said, pushing these notebooks for all of you to learn if you are relatively new to the field. Last week we spoke about a lot of things. We talked about Bayes theorem. We talked about a lot of stats basics. We looked at a lot of distributions and what does probability theory look like. This was the coverage for last week. I'll probably repeat it this time, even in a more rushed manner, just to brush things up. It's winters already, and my chai usually goes cold halfway through, and I always forget that. So apologies. But I'll be taking more breaks today. So we talked about probability theory. It's a mathematical framework for representing uncertain statements or uncertain events. This is relevant for deep learning because if you're working with reinforcement learning, you're quite literally interacting with an environment where you don't know what's going to happen. There's a lot of uncertainty involved. Or ideally, you're also trying to create a function or an algorithm that approximates the world, broadly speaking. and there are also a lot of uncertainties involved. So either ways, you are working with probability and you're working with fractions or percentages of these. There are three types of randomness: inherent randomness, where some randomness exists inside the state, the um, I want to say the system. There's also incomplete observability, where you can't know what's exactly going to happen. And there could also be incomplete modeling. So let's say you're driving on the road, you can't model the future literally. So there's also incomplete modeling. We learned about frequentist probability. We also learned about Bayesian probability. Both are related to how often do events occur, and the other one is how qualitative levels of certainty occur. We learned about random variables, which could be discrete, continuous, or categorical. And the way of representing these can be, for discrete ones, mass functions, and for continuous ones, there's density functions. So these represent the behavior of the said random variables, or RVs. We also learned about marginal probability, which is a distribution over a subset. And it's quite literally derived from the fact that you're calculating these in the margin of your notebook. We also learned about conditional probability. So there are constraints about X happening given Y. We had learned about that last week. And we had learned about all these three terms. So what is expectation, variance, and covariance. We learned about the formula to derive these, the formula to calculate these, and how do they differ from different distributions. We also learned about information theory and how events should be represented in memory. What's the ideal way of doing that? And a few more terms around that. So this is what we had covered last week. So that was for a brush up. For this week, so here's the plan. I'll summarize the chapter. I'll highlight things that are worth rediscussing or emphasizing. After that, I'll share my screen and go through the books portion where I've highlighted different things. And you're welcome to stop me anywhere or ask anything related to anything I'm discussing, or if you read the chapter ahead of time. So this chapter talks about numerical computation. And as we've learned in linear algebra, we're always dealing with numbers. And we are always dealing with numbers whenever you're writing code for machine learning algorithms or deep learning algorithms. There's a large problem with that. It's hard to represent numbers properly inside a computer's memory. By that, I mean there's a constraint on how many digits can exist inside your system's memory. By that, you literally mean RAM, or your GPU RAM. So this means you're always approximating in some way, which means there's a probability of overflow or underflow happening. What is that? When you round off numbers, when you approximate numbers. So when you're working with different numbers, let's say you're working with small numbers and you start rounding them down to zeros, or if you're working with large numbers and you keep rounding them up or keep rounding them up to infinity, underflow or overflow occurs. So underflow happens when all the numbers converge to zero, and overflow happens when all the numbers tend to infinity. So it becomes a very large number. This is we'll come back to this, but this is relevant when you're performing chain of computations on different functions, different inputs. So that's when you need to know how to perform, how to constrain these things, or how to make sure the set doesn't happen. So you need to make sure that things don't always become zero, or things don't always become infinity, because that defeats the purpose of all your computation there. So these are just introductions to different terms that are mentioned throughout the chapter, and all of these texts that I mentioned here are mostly derived from the book. So credit to the book. These aren't my definitions. I just summarize the chapters from the book. Conditioning is how rapidly a function changes with respect to small input change. And the function that we want to minimize for an optimization is called criterion, loss function, or objective function. The thing I learned today wasn't the above point. It was the point that these are usually denoted with a star. So the function you're trying to optimize, or the function that you're trying to minimize or maximize, is usually represented with a star. Um, Good evening from Maharashtra. Good evening to you. I was having vada pav last week. Um, Gradient generalizes the notion of derivative to the case where the derivative is respect with respect to a vector. So you calculate the change of function with derivatives, which give you the slope of how fast is the function changing. And second order derivatives, which means you take a derivative of a function and then you take the derivative of it again, tell you how fast does the first order derivative change. And using all of these computations, you derive different things that tell you the behavior of the said function. So when you're doing this with respect to vectors, that is known as gradient. Sometimes you need partial derivatives of a function whose input and output are vectors. So this could be literally anything. Substitute vectors with matrices in your head. Substitute that with numpy vectors. So think of any function that takes numpy vectors. Most of them would be that. And sometimes you have to calculate partial derivatives of these. So the matrix containing all of these partial derivatives are Jacobian matrices. I've always I've always dreaded the term Jacobian because it's quite hard to mathematically calculate. But in NumPy, you can just call np dot gradient and work around that. But now we all know what Jacobian is. When multiple input dimensions are involved, so all of this is again to analyze the behavior of the input space or the output space or the gradient space for a neural network. Basically, you want to see where the local minimas or the local maximas occur, and that is done through taking derivatives. So, a derivative tells you how fast is the slope changing of a line, and using that, you can say, okay, this could be a local minima, local maxima. That is where these matrices are involved. So for me, it was quite interesting because this is where the linear algebra bits and this is where the probability bits also start coming into the picture. Can we have a session on DFL competition? So this is this is a separate request, by the way, to people who are not aware. I also live stream Kaggle Top Solutions, and this is with respect to that. I'll do that for sure. From what I know, the competition hasn't completely ended yet, so the scores are yet to be finalized. But that's the plan. So that could be the live stream for January 1st. I live stream that every Sunday. By the way, for people that don't know. Thanks for the request, though. I definitely plan to live stream that, and hopefully also get Philip to help me with that. Um, so I was talking about partial derivatives and where these matrices are involved. When you have multiple input dimensions, I'm looking at the third point, by the way. When you have multiple input dimensions, you are probably working with second order derivatives to understand the behaviors. And that quite literally is known as a Hessian matrix. So all of the second order derivatives collected together, which allows to analyze the dimensions or the curvature of dimensions with matrix properties, is known as a Hessian matrix. Why is this interesting? Because I'll go through the book after this, but you can decompose the matrix into eigenvectors, eigenvalues, right? If you remember that. So it's hard to imagine multi-dimensional spaces. You can look at a line and you can tell where it's minima or maxima. You can probably do that with a 3D space as well, right? If you see a 3D visualization. But for higher order dimensions, it's hard to visualize that. So there's no easy way of like picturing that in your head. That being said, Hessian matrices allow you to analyze that, and you can decompose them into values and vectors, right? If you remember from our previous live streams. So using those values, using those decomposition, you have some properties which allow you to check if it's a local maximum or a local minima, given some constraints. So using those decomposition, using those properties, you can tell, okay, this is a local maxima and this is not an local max. Is it a local minima or a global minima? You can use all the properties for that. So the first point we started discussing was you're working with overflow and underflow. And when you are doing that, there's a optimization required inside the algorithms as well. So the framework creators in the book they talk about Theano, but you can think of any framework. The creators of such frameworks have to work with a lot of edge cases. But for the sake of mathematical analysis, if you like trying to analyze a function, you can restrict derivatives to a certain limit, and you do that by applying the Lipschitz constant. So the idea is to work in a constraint where the function doesn't change very fast, and then you can analyze its properties. The topic in the book after this is constrained optimization, where you want to work with a small set of input values and find the maximal or minimal values of the function in that interval. So this is all I wanted to summarize from the chapter. Now we'll start going through things I wanted to highlight from the book. So let me share my screen to that. This was a quick overview of the chapter. So you learn about how to take derivatives, what they do, what do derivatives tell you when you take a derivative of a function, and how can you find a maxima or a minima. If you're new to all of these words, you can read through the chapter, but again, I won't be emphasizing my time on that because my assumption is these live streams are a summarizing factor for you all instead of a summary for the book. Sorry, instead of a substitute for the book. This is why I shouldn't multitask, because I mix up things that I'm supposed to say and think. Anyways, so as I mentioned earlier, the authors start by saying for all real numbers, you usually incur some approximation error when you represent the number in the computer. And these are just rounding errors, and these can be problematic. Then they tell you when underflow occurs and when overflow occurs. Followed by that, they give you an example of softmax function. And again, they bring up multinomial distribution. So again, I'm ranting here, but for me, we learned about this 1 week ago. I had almost forgotten what this was, but then I looked it up and I was instantly able to remember it. So that's one outcome I have been seeing for myself out of the study group, right? Like normally I would see this, I would look it up, land on the Wikipedia page and give up. That's not happening so much now. So that is good. Restricting derivatives would require multiple experiments. Yeah, there's like different ways of calculating that constant, or I don't know how do you come up with that constant. That's not mentioned in the text, but that's the idea of where you use that constant. So you use the constant L as it's represented to constrain the derivatives. That's how that works. Let me know if that made sense, but I was also new to that jargon. Okay, let me go back to sharing my screen again. So they talk about softmax function, and they say softmax is often used to predict probabilities associated with multinomial distribution. Then they remind you what softmax is and how it's defined. After this, they tell you there could be certain cases where the numerator could become zero or denominator could become zero, and this could tend to zero. So the whole denominator could become zero, and then this becomes undefined, right? So for that case, you can change the definition of softmax like so. And then they claim that simple algebra shows that the value of softmax is not changed analytically by adding or subtracting scalar from the vector input. So this solves the problem of making the complete function undefined. And then they talk about almost all libraries, low level libraries as they call it, should take care of this. So you don't have to personally worry about all of these. These pop up more in mathematical analysis, especially if you're working with things that are already defined. So after this, they talk about poor conditioning. Conditioning refers to how rapidly a function changes with respect to small changes in its input. And they say functions that change rapidly with slight changes can cause a lot of chaos inside computations. Then they give you a function, consider f of x defined like a inverse multiplied by the input. And they say when a has an eigenvalue decomposition, because if you remember that always doesn't exist, and sometimes you have to calculate the pseudo inverse. We had discussed this in the first live stream, I think. Yeah, the first live stream. So assuming the decomposition exists, there's something known as a condition number, which is defined like so. And this is the ratio of magnitude of the largest and smallest eigenvalues. When this number is large, the matrix inversion is particularly sensitive to error in the input. And the sensitivity is an property of the matrix, not the result of rounding error due to inversion. So they say poorly conditioned matrices amplify errors when you multiply them with true inverses. So as I said, for me, my mental model here would be, okay, when you're working with functions, you can use a property of eigenvalues to see how fast would they change when you calculate inverses. And then I won't remember the formula at all. There's no way I'll remember this formula. But when I'm trying to find that mental model, if I see the formula, I'll be able to recollect that, okay, yes, I read about this, and this is known as conditioning, which defines how fast do these things change. I'm not sure if pointing these things out constantly is helpful for you all, but for me, like usually I used to wrote all of these formulae. It's more of a reminder for myself as well to not stress about that. So I said earlier you denote functions that you're minimizing or maximizing with a superscript star. So those could be represented like so. X star is equal to argmin of f of x. After this, they show you different plots and how the derivatives behave in those cases. I'm not going to go over in depth over all of these. I'll mention this very quickly. The derivative of a function is denoted as f dash of x and also represented as dy by dx. This gives you the slope of f of x at a point x. And it can also be represented like so. The derivative is useful for minimizing a function because it tells us how to change x in order to make a small improvement in y. So that's a property we use. They talk about minimum, maximum saddle points after this, which I'm again skipping. And then I've mentioned this in the Steven says it's helpful for me to mention where I struggle to remember the formula. So I'll keep mentioning that, and I hope it's not annoying for others that are watching. Thanks, Steven. I mentioned earlier that you have to work with partial derivatives. So last week we had some great math legends who told me how to pronounce some things. But the earlier thing we learned was dy by dx is the derivative, right? So if you play close attention, and hopefully the video doesn't mess this up too much, the d is like a normal d, right? It's not squiggly or it's not cursive. So this is a normal derivative. But if you pay attention here, the partial derivative has a squiggly or a curly d. So I don't know how you say this. If anyone in the audience knows, please let me know. But I only call it like partial derivative in my head. So when I'm reading this, I know this means a partial derivative. So one more time, the d is cursive here. It almost looks like an a, but it's a d. And this is how a normal derivative is mentioned as a regular dy by dx. The partial derivative is a squiggly d by dx. So what does this mean? This only takes the derivative with respect to the function that you are working with. So it's a partial derivative in the sense that the complete function isn't accounted for. Only the partial function or only the partial variable that you're working with, the derivative of that is calculated. So this is how that is mentioned, and this measures how f changes as only variable xi increases at point x. The gradient generalizes the notion of derivative to the case where derivative is with respect to a vector, and this is denoted with delta x f of x. So this is the gradient. After this, they talk about directional derivative in a direction u, where u is a unit vector. It's the slope of the function in direction of u. In other words, the directional derivative of the function with respect to alpha evaluated at 0. So if you apply the chain rule and if you do some, Dinesh says it's called del. So thanks for that, Dinesh. So what we were looking at earlier for partial derivatives. Sorry, I keep breaking my flow, but I think it's cool to keep it a live conversation. So this is del according to Dinesh. And Yantran says it's called Dabba. I remember it being called Dell. So I think I'll side with Dinesh today. But thanks for that. So we're talking about directional derivative and applying the chain rule. You can see that del by del alpha, I'll call it del, of f of x plus alpha u evaluates to u transpose gradient of f of x when alpha is equal to 0. And then they talk about different optimizations. So the cool thing for me here was I always, Vidyasagar, I'll come to your question. I always freak out when I used to see these double pipes and whatnot, and especially deltas and different things. But now, if you remember, this is an L2 norm, literally. So this represents that, and this is the gradient. So over time, what I am noticing for myself as well is as we go through this book, I can understand these terms a lot better for myself. I never would remember this derivative or this function, but I would only have the mental model and I'll remember how things are represented. Basically, it talks about how you can calculate the steepest descent or how you calculate gradient descent. Let's take a look at Vidyasagar's question. So the question is an amazing one. If derivative represents slope of a function, then what does a partial derivative represent? The claim there, Vidyasagar, was you're working with multiple inputs. So that's why I complained about how do you visualize high dimensions, right? You can best think of 3D, but after that you cannot. So when you are working with a function where x is the only input, it's easy to visualize things. But what if there are multiple different things that are changing in the input? Then it becomes a higher dimensional problem. And in that case, let's say you're only working with x at first, and then you're working with z, and then you're working with another input. So you'll only calculate the partial derivative of one by one, all of them, and then calculate the Jacobian matrix and use its properties. I hope that made sense. So partial derivative is helpful when you have multiple input variables and you are dealing with higher dimensions more than 3. So they talk about learning rate, they talk about line search, they talk about a lot of things which are important in context of machine learning. I'm skipping that because these are really straightforward. So ideally, you should spend time reading the chapter if you're new to all of these. They say although gradient descent is limited to optimization in continuous spaces, the general concept of repeatedly making a small move toward better configurations can be generalized to discrete spaces. And ascending an objective function of discrete parameters is known as hill climbing. So for those of you that also watch my Kaggle live streams, we cover this a fair bit there, and you would be aware of that. Now they talk about the Jacobian and Hessian matrices. And this is specifically if you have a function that maps from real numbers m to real numbers n, The Jacobian matrix belongs to this distribution is given like so. So every I comma jth element of J is derived by calculating del by del xj at f of x of I. So you're for me it was easier to like actually write a small matrix down with a function and calculate that. Uh, if you can visualize I comma j in your head and understand that these are different elements, that's also totally cool. So depending on your mental model, you can proceed as you want. After this, they talk about second derivative. And let's say you're working with a derivative of x of I. The derivative of the same with respect to j can be written like so. So this is del square by del xi del j of f. In a single dimension, this is represented as f dash dash x. And this tells us how the first derivative will change as we vary the input. This is important because it tells us whether a gradient step will cause as much of an improvement as you expect based on the gradient alone. And this is measuring curvature. So they give different plots of negative curvature, no curvature, and positive curvature. The subtext explains it really well. Here's the definition of Hessian matrix. So when R function has multiple input dimensions, there are many second derivatives, and these derivatives can be collected together in a matrix called Hessian matrix, represented by capital H of f of x, defined like so. So Jacobian was the first order derivative, and that collected all of those for multi-order inputs. Hessian calculates that in second order. So it's one order above Jacobian matrix. That's my mental model here. Anywhere that the second partial derivative is continuous, the differential operators are commutative, which means their order can be swapped. And this implies that hij is equal to hji. So it's symmetric at such points. So this is one way of analyzing the said functions and their behavior. So they say most functions we encounter in context of deep learning have symmetric Hessian almost everywhere. Because the Hessian is real and symmetric, you can decompose it into a set of real eigenvalues and an orthogonal basis of eigenvectors. The second derivative in a specific direction represented by a unit vector is represented like so, where d is an eigenvalue of h. So this is again another property of how you can decompose this or how you can represent these. Then they talk about different optimizations and how you can calculate again different functions with these. These took for me honestly these took a fair bit amount of time to wrap my head around, but these are quite straightforward. It's only the representation that slows you down. So there are different approximations that you can apply and come up with different properties. After this, they say in multiple dimensions, you need to examine all second derivatives. And using the eigen decomposition of H, you can generalize second derivative test to multiple dimensions. At a critical point where delta is zero, you can examine the eigenvalues to determine if it's a local maxima, minima, or a saddle point. So that's why all of this is important. And again, Vidyasagar, coming back to your question, if you calculate the second order partial derivatives, you decompose that into eigen values and eigenvectors. And using the behavior of those, you can analyze or you can tell how the function will work in such cases. And this is an example of a like 3D point. But as you can see in 4D, 5D, 15D, 20D, it's impossible to like know how this or visualize in your head how the space would be. So that's where these become relevant, for example. Then there's optimization algorithms that use only gradient, such as gradient descent, are called first order optimization. The ones that use Hessian matrices, and they give an example of Newton's method, are second order optimization. Here's where the constant comes into the picture. So we just discussed this. But sometimes you gain some guarantee by restricting yourself into a function that's either Lipschitz continuous or have a continuous derivative. So these are defined, or these a Lipschitz continuous function is a function whose rate of change is bounded or defined by the constant. Do you call this lambda? If anyone can, is this capital lambda, or is I'm just calling it an L? So if anyone can correct me, please. But it says for all x and for all y, the absolute difference between f of x and f of y is less than equal to the constant being applied to their L2 norm. This property is useful because it enables us to quantify our assumption that a small change in the input, such as gradient descent, will have a small change in the output. And they say it's a fairly weak constraint. Many optimization problems can be made Lipschitz continuous with relatively minor modifications. Then they talk about convex optimization and where these are helpful. So you can read through the paragraph, it's again straightforward. When you want to find maximal or minimal values in some set x, some set s for x, sorry, so a small set s which would come from the input domain of x, but you're only concerned with that set. This is known as constrained optimization, and points x that lie within this set are called feasible points in the constrained optimization terminology. So one example is KKT approach, Karush Kun Tucker approach. It provides a very general solution to constrained optimization. And here I again actually learned the first time what this term means. So I've seen this a few times, but they say they introduce the function called generalized Lagrangian or generalized Lagrange function. This is defined with the help of S. So you need to describe S. S is again the constrained input set. So use that in terms of equations and inequalities. So we want a description of S in terms of m functions gi and n functions hj, sorry. So that S is defined like so. X is given for all I. It's the condition is g of I of x is 0. And for h of j of x is less than equal to 0. The equations involving g of I are equality constraints because it's measuring equal to 0. And the inequality are inequality constraints. This allows us to introduce lambda I and alpha j. And the generalized Lagrangian can be defined like so by introducing these KKT multipliers. So you take f of x and you add a function, or you add a variable lambda I to the equality constrained function, and you add alpha to the inequality constrained function. For the record, if it's if it's helpful, I'll again make myself stupid in public, but I'm using the word equality constraint, inequality constraint very fairly easily. That wasn't true until 2 weeks ago. So I did read this chapter thrice before I actually was able to remember it. Um, if you feel that was rushed, go back, rewatch that bit, or just read the text a few times. And then you can solve these problems, or you can have one feasible point where f of x is not allowed to have infinity value. and you can calculate by applying different constraints. So you can read through all of these and you will have a fair bit of understanding of how you can apply these constraints or how these Lagrange multipliers are important. You say a constraint hi of x is active if hi, where x is it as x is its x is at its inflection point, which means its maxima or minima. If this function is equal to 0, that means it's active. And if a constraint is not active, then the solution to the problem found using that constraint would remain at least a local solution if it was removed. So these are again ways of analyzing different functions. A simple set of properties describe the optimal points of constrained optimization problems. These are called the KKT conditions, and these are necessary but not always sufficient for a point to be optimal. The gradient of the generalized Lagrangian, which was this equation we had looked at. So this particular equation that I just tick marked, 4.14. The generalized Lagrangian is 0. The gradient of generalized Lagrangian is 0. All constraints on both x and KKT multipliers are satisfied. And the inequality constraints exhibit complementary slackness. So alpha with the dot product of h of x should be equal to 0 at those points. This is a great question by Rishit. For definition of, sorry, that was the end of the bit I was covering. So I'll come to the question. I was just scrolling to check that. One question for the definition of S. Why is only less than equal to considered inequality constraint? Why not greater than equal to as well? Great question. So from what I understand, this is how these functions are defined. So you're using these to come up with a description of S in terms of the said functions g of I, and so here's g of I, and n set of functions called h of j. So these are by definition written like so, and that is just the name you've given to this constraint. So if this was defined greater than 0, it would still be inequality, but it's just defined as less than equal to 0. So that's a way of defining the said S or the said input where you're trying to apply constrained optimization. I hope that answers your question. Okay. So after this, they talk about least linear least squares, and it's actually cool to see if you just look back on a few weeks. I personally, a few weeks ago, would have thought I don't know what this is, and I would have bailed at that. But the cool thing is you can actually read this and understand, at least for me, more of what this means. So this is calculating the gradient of f of x by taking the transpose of a and doing all of these multiplications, and you're using these properties of multiplying them together. So this is what we've achieved in a way in all these weeks. So you're welcome to read through this example. Most chapters end with a practical example, quote unquote practical. This was that. That's the end of chapter 4. And Rishit says my explanation was satisfactory for him. So I'm happy with that. After this, we were supposed to cover chapter 5, and I've kept it in a title. So I never try to clickbait, so to speak. But I am still not going to cover the chapter. Instead, I'll just point out, sorry, I'll point out different things about the table of contents. So let me head over there. And this is the lengthiest chapter thus far. I don't think if any other chapter is lengthier than this, but this definitely is the lengthiest so far. So here you learn about different things mathematically, and no new mathematical term is introduced. So that is the reason why I'm skipping this. You learn about learning algorithms, where they can be applied, where deep learning makes the most splash. So that's not worth everyone's time, because most of us would know that. You learn about capacity, overfitting, underfitting, all the basics pretty much. So different supervised and unsupervised learning algorithms, SGD, and challenges involving building these deep learning algorithms, or how do you build a machine learning algorithm. So instead of covering this today, I will cover all three chapters that are now pending. So 3 until 6 in a Pythonic fashion next week. I might also just cover 6th like that. So just use Jupyter notebooks for that. Again, you can keep an eye out on the repository, and the notebooks will be pushed there, so you can run through those before next live stream. The plan for next week would be to wind up until the end of chapter 7. And as a reminder, we're reading until the end of chapter 10. So let me mention some homework. And before that, I have a question for everyone. So next time we meet, that we're supposed to meet, will be 31st of December. And if you all are interested in joining at that time, I have nothing better to do with my time. But would a live stream at that point time still be relevant for all of you, or do you want to move it a week ahead? Because I know many people, I recognize the names, join us every week. So if I hear enough yeses, I'll do the live stream regardless. You can always watch the recording, but it's fun to keep it interactive. So let me know if you'd like to skip it a week ahead, or if you'd like to meet again next week. But the plan is to cover everything until chapter 7. So please do let me know. I'm looking at the chat. I'll take a decision today. And in the meantime, let me suggest some homework for the chapters we covered. I would say consider exploring supervised or unsupervised algorithms in scikit-learn. That is what is pretty much discussed in the book for chapter 5. I would also recommend calculate writing functions that can calculate Hessian or Jacobian. You'll just need a bit of NumPy magic. And consider reading chapter 4 to 6. If you want, you're welcome to send a PR to the study group repo. And consider subscribing so that you can be notified for the next meetup. Anirban says he's doing all that I mentioned on Google AI residency. That's pretty cool, Anirban. So are you part of the residency already, or are you preparing for it? Everyone is saying it's cool to meet on the 31st. So awesome. Looks like we'll be studying math as the year comes to an end, and nothing will change next year either. Could we briefly cover capacity? Sure, let me share my screen and head over to that section. Andrea is saying skip if possible. Hmm. Okay, let me still think about this. um, so this was section. We want to tell what is capacity to Rishit. So that's what we're doing now. It's section 5.2. Let's head over there now. I haven't highlighted anything here because I didn't prepare to share my screen, but we'll read through this and try to summarize it ASAP. And as you can see, so this is linear regression in the chapter. I assume all of us know what linear regression is, how you work your way around that. It's cool to represent it like so and work with it. And we already know the tools of how to work with that. So that's why I'm skipping covering these bits. But if in some ways I'm glad that I didn't read this book all the years ahead. I was actually telling this to someone today, because if this is how you define linear regression, right, and I've already lost where it was, I would have given up really early, because that's really scary, right? All of that. So if you tell me that this is one of the most commonly used functions in the field, I'd be like, no way I'll be able to work with this. But now we know better that that's why I also start with notebooks and also try to cover those eventually. That you need a Pythonic analogy to all of this. So all of that ranting to discover capacity. Let's see where it's mentioned. We can control whether a model is more likely to overfit or underfit by altering its capacity. Informally, a model's capacity is its ability to fit a wide variety of functions. Models with low capacity may struggle to fit the training set. Models with high capacity can overfit by memorizing properties. So it basically would depend on the number of parameters or how parameterized is your so to speak learning algorithm. So I would assume, let's say if you are working with simple neural networks or simple feed forward neural networks, if you add a lot of layers, you could overfit. And that model would have a larger capacity, but more capacities to mess up. I hope that answers your question. I am just looking at the chart and catching up. So, okay, some homework that I've already mentioned. You're also welcome to join the community and discuss here. Shout out to Anirban, who had already joined here and introduced himself last week, I think. So you're welcome to keep the discussions continued here or in the comments wherever you want. And apart from that, there's the GitHub repo, which I've already mentioned. And if you're interested in being a part of the Kaggle live streams that I do every weekend, consider subscribing. That's tomorrow at this time. For the live stream, I'll probably tweet about it. So you can see my Twitter username here, but I don't have anything better to do on the 31st. So I'm okay either ways. But I'll probably tweet if we're meeting next week. I'll announce that, since I want to make sure that one and Andrea doesn't miss out, since they're mentioning that she wants us to skip. But okay, we'll keep an eye out for that. Thanks for joining me this week. I'll push the notebooks for all the 3 chapters. We'll cover that next week and also cover 2 chapters. And from here on out, we're starting to learn about different deep neural networks. So it's supposed to be more exciting, but it becomes more math heavy in the book. We'll see how that fares. Thanks for joining. I'll see you all next weekend or the weekend after that, depending on howsoever we decide. And a Merry Christmas in advance to everyone.